Okay, so we're going to take a look at a couple of examples. You can see we have a float here called temp, and I initialize that to 3. And here I simply print that out. If I run this, you can see that prints out 3. Okay, so what if I do something like 1 divided by 3? Okay, if I run this, you'll actually see that we get 0. And that has to do with this operator and the values or variables that are next to that. And it has to do with conversion. Basically, we have 2 versions of these operators. Now, remainder, you remember, we have the remainder for integers. This is for integers. So if I compile and run this, this will actually work. And that's because these to the side of this operator are integer literals. We might look at this, but really we need to look at what is to the left and to the right of the operator. So if these were floating point types with a decimal point, 1.0, we can simply add a 0.0 and something like this. All of a sudden you can see we get squiggly lines here. Try and build and run this, we get errors. And you can see that operator is illegal. Left operand has type double, right operand has type double. But another thing you should note here is you might say, okay, well, this is type double. How does that work? Because here we specify this as a float. Again, you have to look right here and not to this stuff. And that is only declaring a variable called temp of type float. This here will calculate, and whatever this returns will eventually then get assigned to this location, basically. So I have to concentrate solely right here. Okay, so again, this is double. You might expect this to be a float. So how do we differentiate, not just in C++, but in some other programming languages as well, between a float and a double? Well, what we do here is we type f. So we have a value like this, and then we simply do f at the end. I'll write a lowercase f. If I try and compile and run this now, I'll just say no, because we'll still get errors. You will see illegal. This operator again is illegal. The operator has type float. And that is both the left and right operands. So here and here. So that again is how we differentiate in C++ between floats and doubles. So double precision. Now I would like to note that double precision is kind of the standard. So, but you can use float, of course, if you want to use less memory and stuff like that, and if you don't need that extra precision. Okay, so let's actually change this here to something that is legal. So the division operator is legal. I'll do 3.0. And if I compile and run this, Control and F5, you will see what we get a value that we expect. 0 point, and then a bunch of 3s like this. Now if we do, so 2 divided by 3, what we would expect is, again, that will get rounded up right at the end. That final value there will get rounded up to a 7. Of course, you lose the rest of the values because this will go on. This will continue, but we lose some of those values and some of that precision. Now, I would like to note that you'll get kind of the same results. So if I do double, and I'll just remove this, of course, this is a double now. Control F5 to run, and you'll see you'll get the same value. And you might expect more of these digits here, but I will talk about that in a bit more detail later, like why. So for the most part here, we will be using float because this has to do with how many digits you will get before the computer will convert that into floating point representation or scientific notation, basically. You'll see that is 6 or 7, depending on what you do. So here again, we will get about 7 digits, including the one to the left here. We can also store these literals that are in floating point representation. We can also assign those to a variable, and initialize the variable that way. So something like 1.3 and then E, and then maybe something like 21, for example. If we run this, you'll see that is the value that we get, okay? And that is because the computer understands that literal. It can initialize this variable with this literal, even though it is written in floating point representation. We can store values like this. So we have that integer, for example, and we get a value like this now. You can see you can remove a few numbers. So it will store this many digits before it turns that into floating point representation. Like this. It will kind of round the final digit there before the E. And of course, it will do that 10 to the power thing. So here we have a positive because it has to move the decimal point to the left. Here you can see 8, right? 1, 2, 3, 4, 5, 6, 7, 8, as you can see. Okay, and we can add the decimal point over here. So just playing around with a couple of numbers, and you can see again it'll round that final one up, that final digit, and basically you will lose the rest. So this basically has to do with the precision that I mentioned previously. If you do a small number like 0. Something like that and run this, you will see that we now get a negative, so minus 11 in this case, and that's because that decimal point now has to move to the right. Okay, 11 spots before it reaches this spot right here, between the 2 and the 3. So just a couple of examples of what you can expect when you use floating points and how that will convert that to a floating point representation. Okay, so a bit more on conversion. In this case, what I'll do is I'll create a float called enemies per player, and I'll create 2 integers. Enemies wave 1, let's set that maybe to 7. And enemies wave 2, I'll set that to 6. And let's say we have 2 players here. We'll assume just for this example that we have 2 players. Of course, you can do a more complicated program where you input how many players you have and then, store that in a variable and stuff like that. But in this case, just for example here, this equals enemies wave 1, enemies wave 2. Okay, so I'll add those together and then I'll simply print this stuff out. Yeah, and actually I have to divide this by the amount of players, of course. So first we'll add these and then we'll divide by 2. So I'll just run this and we'll see what happens. You'll see we get 6. And this might be confusing because we have 7 plus 6, 13, and this is a float. And that's because we have something called implicit conversion. We are basically converting this to a float. And of course this version of the division operator, since this will use integer division in this case, it will throw away the fractional part. And that's why we get 6 instead of 6.5, for example. If I do 0.0 here and I try again, you will see that all of a sudden we get the correct answer, 6.5, because it now uses the correct division operator for floats. So if you have an integer and a float, then it will use the float version of this division operator instead of the integer one. If both are floating point numbers, then it will use the floating point again. If both are integers, then of course it will use the integer version of that division operator. If I run this, Ctrl F5, or bold this, then you'll see you'll get this warning. And in the output you can see we get this warning: conversion from double to float, possible loss of data. you can click on this here. You see warnings, errors, and that stuff. You can click on that or click on the error list, and that should open up the error list if that was not open previously. Then again, you get this warning. Okay. So what can we do? Well, as I mentioned earlier in the video, is that even though I'm talking about float or floats, you have two versions of those. You have the regular kind of floating point representation, and then you also have the double precision, the 32-bit and the 64-bit basically. And so as I mentioned, to differentiate between those, if you want float, you do an F at the end, and you can just leave it like this for double, which is what we are currently doing, which is why we are getting this error or this warning. It's not really an error, it's just a warning. Okay, we could lose data here. I'll do an F. If we simply go and build this project again, you'll see we get one succeeded. Go to the warning list, and that will clear up. We won't get any warnings in this case. We had a double here, so in the end we would get a double, and we are implicitly converting that to a float. So of course, if you go from a double to a float, you will lose some data. So I'm going to remove that if there, and we're going to look at another way of avoiding this warning that we get. And in this case, we'll go ahead and we'll add these two together and store that in another variable. And so what we can do is we can do another float, add a float sum. Here I can do sum is equal to, and then I can cut this stuff out. And then instead of doing 2.0, I can do sum. So what we are doing here, we are adding two integer variables, and we are storing that in a float. Okay, so that is implicit conversion. And again, we can run this. Again, we'll get 6.5. Another thing we can do, comment this stuff out, and we can do explicit conversion. I'll copy that, paste that right here. You can see that this will work, but the problem is, as we've seen previously, this will give us the wrong answer right here. It will give us 6. So what we can do is we can place that between brackets like that, and we can do float. So this is almost like a function, as you can see. We have float and then we have the parentheses, and in this case we are putting something inside of that, and this will calculate, and whatever value we get from that, so 13, will be converted basically to a float explicitly. And because that is a float, even though 2 is not a float, okay, we have a float to the left here, so because of that, the compiler will use a floating point, the floating point version of this division operator. So that is again explicit conversion. We are explicitly converting this result to a float. You can also convert from floating point to integer, but of course you'll lose some information, so you'll lose that fractional part, as we've seen before. If you assign some floating point number to an integer, again, you lose the fractional part, and the same thing happens whether it's implicit or explicit. Okay, so it's a silly example. I just wanted to highlight the conversion here. Again, implicit like this. You store two integer variables into a float, and this is explicit conversion. We will talk about conversion again in more detail in future lessons, and we'll also talk about float and double again in the second module of this course. But for now, I think we are done with the basics of floating point variables.